Good evening, everyone. It is Wednesday, the 21st. I ate an entire Little Caesars pizza, and I don't feel the best. So, who knows? Today, I'm covering stacks and queues. I'm throwing them in the same video just because they are so similar. And the PowerPoints, once you kind of go through them, you'll see that, oh my gosh, they're the exact same thing, just handled differently. So, to begin, a stack is a linear data structure where elements are stacked on top of each other. The best, thing I can point to is like a stack of plates. Stack data structures are useful when order matters, because as you add and remove to the stack, it ends up reversing them. Stacks ensure that a system does not move onto a new action before completing the actions before. So, in a stack data structure, items are added and removed from the top of the stack. This makes it last in, first out. You'll hear this a lot, LIFO and FIFO, first in, first out. And be sure to know the difference between these two. So, the way we're going to add and remove from our stack is push and pop. So, push is going to place an item on top of our stack, and pop is going to remove the item at the top of the stack. For our stack data structure, like I said, a stack of plates. Ooh, no clue what I was writing there, but I'm probably spitting. So, if we have a stack of plates, let me just draw one. Plate, 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 and plate. This is going to be plate 0, plate 1, 2, 3, and 4. If we want to add a plate to this pile, we're going to have to add it to the very top. So whenever we add it, we're going to have 0, 1, 2, 3, 4, and 5. And if we want to remove, we have to get rid from the top also. So if we want to remove the plate we just added, this would be push 5, and this is going to be pop. So this is going to get rid of plate number 5. We just go ahead and erase it. And then most of the time, pop is going to return a value. So equals my val. So if we were to take from the bottom of the stack, but add to the top, this would be FIFO, so first in, first out. This is how queues work, but we'll touch on that later. So, a couple of common operations with your stacks. You're going to want to be able to push and pop. You want to see what's on top without changing anything. So this is where peek comes in. We're going to have isEmpty and getLength as always. And now we can kind of cover, hey, why do we care about stacks? What do they matter? So by default, whenever you add and remove to a stack, it's going to reverse the order. So if we come over here, we have the string hello. We go through the string, and for every letter, we push something onto the stack. So our stack is going to have H, E, L, L, and O. You can draw boxes if you want. There we go. That's a horrible box. And so now we're going to pop from this stack that we made. So first, the O would come out. So the O is gone. Next, the L. Then the other L. Perhaps. The E. And then finally, the H would come out. So we would do something like push H, push E, push L, push L, push O. And finally over here we're doing pop, 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 and pop. So if you'll notice, whenever we originally had this string, it was correct. And then whenever we pop it from the stack, it's in reverse. A big thing that stacks are used for, surprisingly, are the undo and redo feature. So every time you change something in your program, that state is pushed to a stack. If I were to come in and make this text smaller, the original size, or the slide containing the original size, is pushed to the stack. If I want to go back to it, I just have to pop it from the stack. And we're back at full size. We have maze solving. This is actually a pretty cool one. I'm going to steal this image, hopefully. Yeah. So, we can solve mazes with a stack. Albeit, it's not the intelligent, perfect every time one, but it works nonetheless. And the idea behind this is that every decision we have to make, so in this case we can go left or we can go right, we push our decisions onto the stack. So I'm going to make a big old bucket for my stack. First, I'm going to say, okay, once I finish, I want to go right. But for now, I'd like to go left. And so we take this path. I'm going to index this as decision 1, and this one's going to be decision 2. Here, we can either go straight, or we can go to the left. I'm going to go ahead and push left, 2, and I'm going to do straight 2. So I'm going to follow this path. Oh man, it hit a dead end. Good thing we have a stack. So we are going to pop straight from the stack. So straight 2 disappears. We finish up with everything it had to do. And now we follow the second path. And we do this for every decision we make. We could go right, we could go left, pick one, push the other to the stack. And then, finally, your programming languages work as a stack. Whenever we call main, the main function is pushed to the very bottom. And every subsequent call after that, we add the calls to the stack. So whenever the add call finishes, it's going to return where we were in average and pick up like nothing happened, this time with some new value. Once average finishes, we're going to return to main like nothing happened, right where we called from. So a couple different ways we can implement stacks. If we want a static stack, we implement it with an array or a vector. If we want a linked list as our base to the stack, it's going to be a dynamic stack. The reason we choose this is because if you'll remember, stacks and queues are adaptive containers. They can't stand on their own 2 feet, and they need the other containers we've seen to do this. Meaning, yes, you could make like a map stack. Who knows? So, as with any linked list, doesn't matter if we're implementing a stack, we still need a head node, and most of the time a tail node. If we want to add to our linked list, we're going to push an item to the head node, and if we want to remove from the list, we're going to pop an item from the head node. We can look at stacked linked list .cpp. We can see, like, at its core, it's a linked list. We have our stack node struct, which takes a value. I picked the wrong one, didn't I? Yeah, I did. Whoops. We've got our list node struct with a double as the value and a pointer to next. We have a pointer to top. And then we have the functions that I explained earlier. Is empty, get length, we can push a value, we can pop a value, and we can peek a value. So since the stack needs to push and pop from the front, everything we do is going to rely on the head node. With our push, we're going to create a new list node. We're going to check if top exists, and if it doesn't, we assign the next element in our node to top and scoot top over. So if I have a list A points to B, points to C, and I want to add something to the front, but I want to use a stack, what I'm going to do is scoot a node into place. So create a node, it's going to be Z, have it point to head, and then scoot head over to Z. And that's it. That's all we have to do to insert into a stack linked list. If we want to pop from it, we have to work backwards. So we go at the top, we check if the top is by itself or not. We scoot node pointer's value into temp, and then delete node pointer. I may have lied. So node pointer is equal to top. We put node pointer's value into temp, and we return temp. Apparently this does not update top. Oh, top is equal to top's next. So, goodness gracious, I need to read my code more. If we want to remove Z, if we want to pop it from our stack, what's going to happen is we're going to put a pointer right here. We're going to say, hey, does pointer have a next value? If it does, we scoot head down. We return, or delete the node, and we return Z. And then we can also print the stack if we really want to. And then it's our good old favorite fashioned, yeah, linked list program. We cd into stack examples. So what's going to happen is we're going to push 3 values down, 2.5, 7.9, and 12.6. Since we push 2.5 first, it's going to be at the bottom. So our current stack, it has 12.6 at the top, followed by 7.9 and 2.5 at the bottom. Whenever we pop that head node of our stack, 12.6 is the first to go. So whenever we create our stack, it's going to have 2.5 over here, pointed to by 7.9, pointed to by 12.6. And if you want to draw it vertically, you can. So it's going to have 2.5, 7.9, 12.6. Whenever we want to delete 12.6, we're going to delete this, scoot head down, we pop this, so our new head is 7.9. So, it's just linked lists with a little change. We can also template it, which I'm sure you've already done with your program too. But we can take a peek at it. We have a templated type name T. Our stack node takes a t value, and then outside of that, it's the same. If we want to push, we create a new stack node, and we add it to the top. If we want to pop, we make sure the stack is not empty, scoot top down, and then delete the head. Yeah. So this one works with strings. I believe that these are not defined, so I'm going to... We'll see this program again. Do not worry your little heart. But all it's going to do is ask for a couple of items and then print them back out. So that brings us to our static stacks. So the array implementation of these are actually kind of cool. I probably wouldn't have been able to come up with it, but it is this one. So, looking at our main first, we are going to push 5, 10, 15, 20, and 25, and then we pop 5 values. So if we look at what we add, pizza. If we look at what we've added and work our way in reverse, the values that are going to come out are 25, 20, 15, 10, and 5. Within our .h file, we have a pointer to a stack array, a stack size, and then an integer that indicates the top of our stack. Constructor just dynamically allocates. So this technically copies one stack array to another. I have yet to find a use. And then if we want to push and pop from our stack, we're going to go where stack array is at top index and add num. That's it. If we want to pop, we're going to go that same spot and return it. So I can draw it out for you. I'm going to do the horizontal, so we have an index here. I'm going to say it is 5 values long. So at the very beginning, top is equal to -1. If we go to push our first item, we're going to increment and add to the array. So top is equal to 0. Increment, add to the array. And we're going to repeat this process. Then whenever we want to pop, we work the opposite way. So we're going to pop. This is going to return 25 because top is currently at index 4. Delete that. We pop again. Returns 20. And this process goes back and forth until we hit 5 and we are out of numbers. So we are adding to the end of our array and then removing from the end of our array. So looking at it run, we push 5, 10, 15, 20, 25, and then whenever we go to pop, we pop in reverse. So that's not bad. I'm wondering what the catch is. We can template the stack array, just like we did the linked list. And oh my gosh, you've seen this before. We're going to have the user input some strings and then output them. How big should I make this stack? I'm going to go with 5. I want to push an item. Top 5 states to live in. Tennessee. Missouri. And then 1738. That's the number one state, 1738. So we've input 5 strings onto the stack, and whenever we go to push another, it's going to yell at us. I'm going to say, hey, can I put this here? And it's going to tell me, hey, the stack is full. If I pop an item, we get rid of 1738, and now we have 4 items in the stack. We can add to it once again. And then if we pop everything, thanks will come off, 14 will come off, ASDF will come off, misery will come off, then finally Tennessee will come off. If we try to pop with an empty stack, it's going to yell at us. That should not be there. And then finally, we have the stack standard template library. We can access using #include stack, and then we can define it saying stack, giving it a data type within the alligators, and then a name. So we want to take a quick peek at this. Let me clean this up a little bit. We're going to make a stack named S, which has integers. We are using include stack. We push a bunch of numbers down, we print the current size of the stack, and then we can s.top the stack, which I'm assuming is the peak. And then we start popping variables, or popping values. So we push 10, 30, 20, 5, and then 1, and then we pop in reverse values, so 1, 5, 20, 30, and 10. So that's everything you really need to know about stacks. I still suggest, and will always suggest, looking it up if you have questions, or email me. Stack Overflow if you want to get yelled at, and Zybooks. That would also help. So next we're going to look at queues and decks, and you'll see a lot of this is the exact same. So in a queue abstract data type, items are added to the end and removed from the beginning. So it is FIFO, or first in, first out. Within our queue, we want a way to push and pop. If we push, we add to the end, and if we pop, we add to the front. The best example is just waiting in line. Maybe it's at a supermarket, maybe it's at McDonald's drive-thru. But regardless, the person in the front of the line will leave first. Person in the back will leave last, because they have to wait their turn. A couple of common operations with a queue. We have NQ and DQ, which is how we add and remove items. We can peek and see, hey, what's at the front of the line? Then we have isEmpty and getLength, like always. So, holy moly, 2 types of queue implementations, a static queue and a dynamic queue. The static is going to be created from an array or a vector, and the dynamic is going to be created from a linked list. With the linked list queue, we need a head node and a tail node because we have to know where the front of the list is and the back of the list is. We can look at the queue implemented with the linked list now. Told you you'd know where this comes from. Queue linked list, and that has nothing in it. Poggers. Oh no, not my fill folder. Lecture chapter 5. Programs. There we go. Because I'm looking at the wrong one, duh. So we can crack open QLL. It's named differently in your ALS code. It's going to be double Q. I'm going to go ahead and compile, and we can look at the .h. So we have a linked list yet again. It has a list node in it with a value and a next pointer, and this one has a head and a tail. It's got a lot of the same old, is empty, get length, and then we also have a push back. So with this we want to add to the end of our linked list. So we are going to navigate. I lied, we're going to push to the head. I lied again, we're pushing to the tail. So we navigate to the end of our list, we scoot tail down, so we say tails next is equal to new node, so we kind of tab it over. We assign new node, or tail equal to new node, and then we say tails next is null. And that's it. We go to the end of the list, and we add it. If we want to remove the item in the front of the queue, we're going to do the opposite. So we're going to navigate to the head, so node pointer is equal to head. We scoot head down, and then we delete node pointer. We also have to return the value, and that's it. We scoot head and blow it up. Holy moly. We've got the same generic linked list program. Gonna run it for you. If you'll notice, compared to stack, this one stays in order. So we push a 2.5 to the front, the back, I guess. So our list is empty. We add 2.5 in. We push 7.9. That's going after 2.5. So we have nothing. We're going to push 2.5 in, points to null. We push a 7.9 in, so we go to the end, which is our 2.5. We set the tails next equal to 7.9, and then we scoot tail down. And we repeat that once again for 12.6. So we add the node in and scoot tail down. I'm trying to think if there's anything else in this. I mean, we make a node and we scoot it. So we have integer queue and queue template. Integer queue, we have a integer value, a front and a rear. If we want to push back onto our integer queue, it's going to be the same song and dance. We go to the rear and we add the new node, and we scoot rear down. If we want to pop the front, we're going to go to the front, scoot head down, and then add our value. This one is going to enqueue 5 values, so 0, 1, 2, 3, and 4, and then pop them off. Since they get popped off in the same order that they were added, we can know that we pushed 0 first, 1 second, 3, 0, 1, 2, 3, and 4. Now that we're kind of masters at queues, queue template, it's going to be the same thing with the type name T. If you want to look at it, you are more than welcome to. Now we're going to look at doing a queue with an array. So let me go find it. Queue array. So looking at queue.h, we have a type T queue array. So whatever we make it, it's going to be a size of that, or an array that can hold that many data types. We have a queue size and the number of items in the queue. So we have a way to say, hey, maybe, or are we at max yet? And then we also have a front and a rear. Oh, is that it? I guess it is. So, looking at our queue, we're going to push a couple of items onto our list. Oh, it's a .h. Duh, it's down here. So for our default constructor, we're going to dynamically allocate enough memory, or S amount of memory for data type T. We're making the array. We set queue size equal to S, so how many items our queue can hold, a front and a rear, and then the current number of items in the queue, which in this case is 0. We also throw in a copy constructor, just in case. But if you want to add an element into our queue array, you're going to increment rear and then add the item into queue array at rear index. So we go to the end, increment, add an item. Wow, that's not bad. If we want to remove an item from the front, we increment the front and we return the item. The big thing that I want you to notice is that we are incrementing both front and rear instead of trying to add and decrement. If you look at this line where we ask if front is equal to rear, we set rear equal to -1. Then if we come all the way down, whenever we clear our queue, we set front and rear equal to each other at the end of the queue. And now we can't access any more of the items. Outside of that, it's not terrible. If I crack open a OneNote, make an array once again, so front and rear are going to start at -1 outside of our array. Whenever we push to it, so whenever we add an element to the end, we're going to increment R and add our element. So R, increment, we'll put it at index 3, position 4. I'm going to put F on the bottom, just so it's a little more clear. And whenever we remove an element, we're going to move F in. So F moves in, and notice how we don't remove anything whenever we do this. If I can find it. There it is. So we say item is equal to queue array at front, and then we don't delete the item. So that item actually stays in memory until we reset or go back over it. Is there a display queue? I guess not. So eventually, whenever we keep adding and removing items, F is going to be equal to R, which at that case, whenever we go to, I'd like to say add another item, remove an item, whenever we do that, rear is going to get set to -1. So whenever F and R meet up, F is equal to R goes back to the start. We act like none of this ever happened. I'm not sure what F is supposed to do to get back to the start. But you know what? I will not question it. If we do a front... Yeah, I have no clue how we get back, but we ball. So where are we at now? Which code is this? This is Q array. Which I was already in. Got it. So, looking at driver.cpp, it's the generic enter names, and we are going to pop them. So if I do Adam, Billy, Charlotte, Deborah, and Epstein, you know, if they're in line at a grocery store or something, Adam will get his groceries first, followed by Billy, followed by Charlotte, and then Deborah, and then finally Epstein. So with everyone that we're adding, we're scooting rear, back, and adding an item. Every time we pop, we scoot front, back, and we return that item. So, Q has a standard template library. You can get to it by using #include Q, and then making one by saying Q, data type, my Q. So we take a peek at somewhere around here. Q standard template library. So we've got this very fancy restaurant that we are taking clients for. It is a Longhorn Steakhouse. We have Clint Eastwood, Jackie Chan, Lee Von Cleef, Charles Bronson, Sylvester Stallone, and Chuck Norris. So if we look at our queue on, you know, who's getting into the restaurant first, it's going to be Clint Eastwood, Jackie Chan, this guy, Charles Bronson, I've heard that name before, Sylvester Stallone, I'm just gonna put Rocky, and then finally Chuck Norris. Whenever the poor waitress who has to deal with them has a table, she's going to come down here and say, "Hey, Clint Eastwood, I have a table for you." Clint Eastwood will go and enjoy his meal. And then Jackie Chan's up next for the table. Whenever the waitress has a table, "Hey, Jackie Chan, I have a table for you." And Jackie Chan gets to go eat. So if we run this program, we can see what happens. So there's currently 6 on the wait list. Clint Eastwood gets his table. 5 on the wait list. Jackie Chan gets his table. There are 4 on the wait list. And then the person at the end of the wait list, Chuck Norris, beat everyone up who was in front. Holy moly. Then there's 1 on the wait list, and it is Chuck Norris, and he gets his table. And then peeking at the code, there is no, dot beat everyone up with our queue. We just pop with a for loop. Looking at q2.cpp, I'm not going to run it. We are going to push back 3 numbers, 2, 4, and 6, and then pop 3 numbers, 2, 4, and 6. This would be great, practice if you want. Yeah. So that brings us to the second half of queues. We have these things called decks. They are double-ended queues. Once again, if you want to make it, #include deck, integer, my deck. But what is a deck? A deck stands for a double-ended queue. You can push and pop from both sides. You get access to stuff like push front and pop front, or you can peek front. You can push back, pop back, peek back. So with the deck, you can both implement a stack and a queue using the same data structure. We can go take a peek at deck. Yeah, let's do this one. So within our deck named colors, we're going to push front blue. So blue is in the very front. Where is it? There it is. So blue is in the very front. I'm going to put it on top. So blue. We're going to push back red, yellow, orange, brown, and then we say, oh shit, we forgot green. Put that on top. So this is going to be what our deck looks like after we add everything. So number of colors in the queue, that's going to be 6. Favorite color from the front of the queue, that's going to be green. Least favorite color, brown. Removing the least favorite color, so we pop the back. Number of colors in queue is going to be colors.size. It is now 5. We pop the front. Goodbye, green. And then we have 4 colors in the deck. So I'm going to run this for you all just so you can see. So we have our deck. We remove green and brown, like I told you. And we have 5 numbers, and then we remove the top one again. Most favorite colors, pop front. I forgot one, right? Now my numbers aren't lining up, but we remove twice from the front and once from the back. So this slide goes into the deck versus the list. It's basically like the deck is a dynamic array versus a linked list. The deck provides constant time insertions and deletions from the beginning and end, but it sucks at the middle. A list is super fast in any position. And then any insertion or deletion in the middle of a deck breaks it flat out. And then with the list, we can add anywhere. So a couple of queue examples. I know this weekend I was trying to play Helldivers. You know, go serve Super Earth. And at the start of the login queue, you have me, the robot slaying Chad. And at the end of the queue, who's getting in first but a guy who's gonna go kill bugs? Enough said. Character input is also a big thing that queues are used for. So within a game, there's going to be some sort of main loop that says, hey, while this game is running, handle events. And these events, at least in this context, are going to be player actions. Walk forward, crouch, emote, walk backwards, jump. So if I press jump, that's going to get added to the queue, and then it will be performed. If I want to walk backwards after I jump, once jump is gone, I can't really scoot it off screen, but you know, once jump is gone, walk backwards will be popped off our queue and performed. And then finally, we have the Foxhole item creation. I don't know how many of you know Foxhole, or if you care, but if you see this funny little word right here, we have a queue to create items. Holy moly. And then I never assigned this in class practice, so you can ignore it. So, goodbye. It's gone. And yeah, that was stacks and queues. I hope you enjoyed watching.